Today we're going to move on to section 11.3, which is areas of regular polygons. Remember, a regular polygon is a polygon that is both equilateral and equiangular. And there's a rule here that says any regular polygon can be inscribed in a circle. That means drawn with every vertex touching the circle. Likewise, any regular polygon can have a circle circumscribed about it. This circle is circumscribing the pentagon, which is inscribed in the circle. I'm going to come back down to all the rest of this in a second. When we inscribe that regular polygon in a circle, we can define some other terms. The center of the regular polygon is the center of the circle that circumscribes the polygon. In this diagram, we had circle O with a pentagon ABCDE inscribed in it. So O is also the center of the pentagon. The radius of the regular polygon is the distance from the center to any vertex. So again, in this picture, we can draw radii from O to A, O to B, O to C, O to D, and O to E. The central angle of a regular polygon is the angle formed by two radii drawn to consecutive vertices. Now, this is a regular n-gon, so every central angle is going to be the same. To find the measure of each one, we take 360 and divide by n. Again, if we go back to this picture, a central angle would be the angle EOD. And in a pentagon, the measure of that angle will be 360 divided by 5, which is 72 degrees. The last term is called the apothem or the apothem. Both are correct pronunciations. The apothem of a regular polygon is the distance from the center to any side. And we remember that when you measure distance from a point to a line, it's always on a perpendicular. So in this diagram, my apothem is the distance from O to this side ED. It's the length of this perpendicular. We use a lowercase a for apothem, and here's the R for the radius. And what you'll notice is that there's an isosceles triangle here formed by the central angle and one of the sides of the polygon. And then there's a right triangle when you draw on the apothem that is the apothem, half the side length, and the radius. How could we find the area of a regular polygon? Every regular polygon can be divided up into these isosceles triangles. And if we look, if this was a regular n-gon, there would be n of those triangles that are all congruent to each other. So S is the length of a polygon side, and A is the apothem for that regular polygon. So this one happens to be a hexagon, but we could do this for any regular n-gon. The area of one of those triangles is 1/2 the base of the triangle times the height of the triangle. The base of the triangle is S, and the height of the triangle is the apothem. For a regular n-gon, there will be n congruent triangles. So the area of the polygon is going to be the area of one of those polygons times n. Now, if I rearrange that, I get 1/2 apothem times S times n. S times n, that's the length of each side times the number of each sides. S times m is perimeter. So there's a formula for area of a regular polygon. The area of a regular polygon is 1/2 the apothem times the perimeter of the polygon. And again, this only works for regular polygons. For some regular polygons, we can find exact values, and we're going to use an example of a square, which in a square, if I knew each side was 4, the quickest way to find area is to do 4 squared equals 16. But if we can follow along with kind of this method, we'll start with a square and then look at other polygons. The perimeter of the square is each side times number of sides, which is 16. A central angle goes from here to there and is 360 divided by the number of sides. In this case, 360 divided by 4 is 90 degrees. This is a right triangle here. The apothem goes from the center of the square perpendicular to the side. Now, that was a 90-degree angle that I just bisected, so what I have here are two small 45, 45, 90 triangles where these lengths are all 2. The radius of the square goes from the center to the vertex. It's the hypotenuse of this 45, 45, 90 triangle. If the leg is 2, the hypotenuse is 2 times the square root of 2. That's the radius. So we could use 4 squared to get the area, but if we use the formula we just learned, 1/2 times apothem times perimeter, we see 1/2 of 2 is 1. 1 times 16 is 16. We get the same answer. Again, you don't have to use that method, but we can see how it works for a square. We can do this with an equilateral triangle. I have an equilateral triangle where every side is 4. The perimeter is 4 times 3 is 12. A central angle goes from a vertex to the center, out again, is going to be 360 divided by 3, which is 120 degrees. Then I'm going to draw in the apothem from the center, perpendicular to the side, and since this is isosceles, it'll bisect that side into 2 and 2. Also, this vertex, the central angle was 120, and when I draw in the apothem, it'll split it into 60 and 60. So here we have a 30, 60, 90 triangle. The 2 is the longer leg, so to find the apothem, I'm going to take this 2 and divide it by square root of 3 to get the shorter leg. Rationalize, and we get 2 square root of 3 over 3. That's the shorter leg. To get the radius, that's the hypotenuse of the 30, 60, 90. Hypotenuse is shorter leg times 2. I'm going to take what is my apothem, multiply it by 2, and I get 4 square root of 3 over 3. To find area, I take 1/2 times the apothem times the perimeter. The 1/2 and the 2 cancel out. 12 over 3 is 4, and I get a final answer of 4 square root of 3. There are other ways to find the area of this triangle, but depending on what you're given, 1/2 apothem times perimeter may be the quickest method. We can also get an exact value if we do this with a hexagon. Here's a hexagon, and I have a hexagon with all sides of length 4. The perimeter is 4 times 6, which is 24. The central angle goes out to each consecutive vertices, and I take 360 and divide by 6 to get a central angle of 60 degrees. So this is a triangle. These two sides are the same because they're the radius, and this top angle is 60. This is an equilateral triangle. So these sides are both going to be 4 and 4. When I draw in the apothem, it divides the side of the hexagon into 2 and 2. The shorter leg is 2 because that's now opposite of the 30. Multiply by square root of 3 to get the longer leg. That's the apothem. The radius is 4. The area is 1/2 times the apothem times the perimeter. The 1/2 and the 2 cancel out, and we get 24 times the square root of 3. So for those 3 regular polygons, we can get exact values. For some, we're going to need to round. And in this case, we've been given this length, 6.5, is the apothem, and the 8 is the radius. It's a pentagon. If we want to find the area of the pentagon, we need to use 1/2 apothem times perimeter. So I need to find the perimeter. I need to find the length of each side. If you look at this right triangle, we have one leg and we have the hypotenuse. To find the other leg, I might call that x, we can use Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. When you do this, you get x is equal to the square root of 21.75. We're going to have to round at the end, but I'm going to wait until I do all the calculations. That's the length of x. The side is going to be 2x, And then this is a pentagon, so there's 5 sides. So the perimeter is going to be 5 times 2x or 10x. So if we plug this into 1/2 times the apothem times the perimeter, I'm going to write all of that out in one step, then put it into my calculator all at once and get a total area of about 151.57. You cannot get an exact value here. In this case, we were given both the apothem and the radius. We can also do this problem if we're only given one length. We're given just the apothem. I can do this because it's a regular pentagon, which means that the measure of the central angle is 360 divided by 5, which is 72 degrees. So if I look and I draw in a radius and this x, which is half of the side, I see that I have a right triangle, and I know that the angle at the center is half of my central angle. This angle is 36 degrees. So if I want to find the side length, I'm going to use that right triangle where I have 36 degrees. I have a leg that's 10.5, and I'm trying to find the other leg. I'm going to use tangent. Tangent of 36 equals x over 10.5. So this is 10.5 times tangent of 36 equals x. The side length is 2x, so we would type all this in my calculator and double it to get 15.26. It's a pentagon, so the perimeter is 5 times the side length, and that's about 76.29. Now we can find area because we have the apothem and we have the perimeter. Area is 1/2 times the apothem times perimeter. And when you put all that in your calculator, you get an area of 400.51. As you go through this section, you will also do some problems where you're adding and subtracting areas, and I'm not going to do this whole one out now, but one suggestion, when you want to find an area of a shaded region, the first thing I would do is write myself just a quick kind of equation of what areas I'm adding and subtracting. This shaded region is everything that's inside the circle, but not in the triangle. So I need to find the area of the circle minus the area of the triangle. I would do each of those calculations and then plug them into this formula, but kind of set yourself up of what areas you need to find first, and then do the calculations and combine them. The assignment is a little bit longer today, but since it's a Thursday, you have tomorrow to work on it as well. We're going to wrap up after 11:3, do some practice for a couple days next week, and do a graded assignment next week.